Welcome to the Deep Sleep Science Channel. Tonight, we'll drift gently through the idea of a world that is small, rocky, and quietly intriguing, circling a dim red star far beyond our own sky. We'll keep everything soft, slow, and simple as we explore TRAPPIST-1e, one calm detail at a time. TRAPPIST-1e is understood to be a terrestrial planet with measurements that fit a rocky body rather than a swollen gas world. Its size is close to Earth's, which is one of the reasons it's so often discussed as an Earth-like candidate. That similarity in scale matters because it hints at familiar surface physics, like how gravity shapes air, weather, and landscapes, even if the planet's environment is very different. TRAPPIST-1e moves around an ultra-cool, low-mass E&D dwarf star, a star that shines far more faintly than the Sun. Because the star is dim, the planet can orbit much closer in and still receive a level of warmth, but models sometimes treat as potentially temperate. This setting is a reminder that habitable distance is not one universal number. It depends on what kind of star is doing the warming. A year on TRAPPIST-1e is only a few days long, simply because its orbit is so tight. That short orbital period places it in a region where gravity and time feel different from Earth's slow seasonal rhythm. The closeness also strengthens the star's pull, making star-planet interactions more intense. Even small variations in orbit can matter more when everything is packed so tightly. The planet's distance from its star is only a small fraction of the Earth-Sun distance, yet that does not automatically mean it must be scorchingly hot. Around a cool star, a close orbit can still land a planet in a range of incoming energy that climate studies consider interesting. This is part of why EM-D dwarf systems are so compelling. Their habitable zones are tucked in close. It creates compact neighborhoods of potentially rocky worlds. TRAPPIST-1e sits inside a famously compact system where several rocky planets orbit closer to their star than Mercury does to the Sun. In that kind of layout, planets are not isolated dots. They are a connected group, tugging on one another in measurable ways. Resonances and near-resonances can shape their orbits over long timescales. The entire system becomes a living example of gravitational choreography. TRAPPIST-1e is known because it transits, passing in front of its star from our point of view. That gentle dip in starlight lets scientists estimate the planet's radius with careful precision. In a system this tight, small shifts in transit times can also reveal the influence of neighboring planets. Those timing variations become another tool for understanding mass and orbital relationships. With an orbit so close to its star, TRAPPIST-1e is a strong candidate for tidal locking, or at least for a very slow rotation. Tidal effects can gradually shape a planet's spin until the same face points toward the star much of the time. That kind of rotation reshapes the idea of day and night into large-scale climate zones. It also changes how winds and clouds might organize themselves. If TRAPPIST-1e is tidally locked, one of the central questions becomes how strongly the day side and night side differ in temperature. Without an atmosphere or ocean to move heat around, the contrast could be severe. With enough air or water, that heat can be shared, softening the extremes. In many models, the efficiency of this heat redistribution is one of the keys to whether surface water could remain stable. Many scenarios link TRAPPIST-1e's ability to keep surface water to what happened during the star's youth. Low-mass stars can be especially active early on, producing flares and high-energy radiation that can strip atmospheres. If gases were lost quickly, the planet might have ended up bare. If it retained enough volatiles or rebuilt them, later its surface could be far more temperate. The TRAPPIST-1 system is about 40 light-years away, close enough in cosmic terms to invite detailed scrutiny. It is still unimaginably distant for travel, but it is near enough to become a regular target for advanced telescopes. That proximity makes it feel less abstract than many habitable zone candidates found much farther away. It becomes a nearby test case for how small planets behave around small stars. TRAPPIST-1e lives under a star that emits light richer in infrared than the sunlight Earth evolved beneath. That shift in color and energy distribution matters for photochemistry, for how surfaces absorb warmth, and for how atmospheres build or break molecules. Even the simple act of illumination would feel different. The spectrum of the star becomes part of the planet's climate machinery. If TRAPPIST-1e's density is rocky and its size is near Earth's, its surface gravity may be broadly comparable to Earth's. Gravity sets the weight of air, the height of mountains, and the way gases escape into space. A familiar gravity scale can make certain processes feel more Earth-adjacent. Still, similarity in gravity does not guarantee similarity in climate. TRAPPIST-1e is often singled out because it is not as intensely irradiated as the innermost planets in its system. That reduces the likelihood that it sits in a Venus-like runaway greenhouse state. Being a little farther out can be the difference between a world that keeps volatiles and one that loses them. In comparative terms, TRAPPIST-1e often appears as one of the more temperate possibilities in its family. If TRAPPIST-1e holds an atmosphere, it may not resemble Earth's nitrogen-oxygen blend. Models explore many possibilities, including CO2-rich or nitrogen-dominated compositions, and a range of pressures. Different mixes change greenhouse strength, cloud behavior, and surface chemistry. The uncertainty is large, but the scenarios are physically grounded in how rocky worlds can evolve. Some climate ideas suggest the planet could be stabilized by clouds that form persistently over the dayside. Bright cloud decks can reflect starlight and limit heating, acting like a protective mirror. On a tidally locked planet, circulation might repeatedly feed moisture into that same region, reinforcing the cloud layer. In that way, weather itself can become part of climate stability. If TRAPPIST-1e lacks a substantial atmosphere, the surface could swing between intense warmth and deep cold. Airless or near-airless bodies tend to heat rapidly under starlight and cool rapidly in darkness. That would make long-lived surface liquid water less likely. The contrast between atmospheric and airless outcomes is one of the starkest forks in its possible story. Tidal forces in a compact system can also produce internal heating, depending on eccentricity and gravitational nudges from neighbors. Even modest flexing can generate warmth inside the planet's rocky interior. That internal energy can support volcanism and affect long-term atmospheric renewal. In some scenarios, geology and climate are linked through this quiet, persistent heating. If the orbit is very nearly circular, tidal heating would be reduced compared with a more elliptical path. A perfectly circular orbit means less rhythmic squeezing and stretching. Yet in tightly packed systems, even small eccentricities can matter and can persist through interactions. The details of orbital shape become surprisingly important for internal energy budgets. TRAPPIST-1e may have oceans if it retained or gained enough water, and those oceans could be global or regionally distributed. Water coverage changes how a planet stores heat and how quickly it responds to changes in starlight. It also shapes the potential for carbon cycling through dissolution and precipitation. Even without knowing the coastline, the mere presence of large water reservoirs would change everything. If the planet has a magnetic field, it could help reduce atmospheric erosion by deflecting stellar wind. Magnetic shielding is not a perfect wall, but it can lower the rate at which charged particles strip gases away. Whether a rocky planet around an M dwarf can maintain a long-lived dynamo is still uncertain. It depends on interior structure, cooling rate, and rotation. The star's flare activity matters because high-energy radiation can break apart atmospheric molecules. that can thin the atmosphere over time or shift it into a different chemical balance. Under some conditions, it can also produce complex hazes that change how the atmosphere absorbs and reflects light. In this way, stellar behavior can sculpt both climate and detectability. Because multiple TRAPPIST-1 planets transit, scientists can compare them as a set. Worlds of similar size can end up with different atmospheres and different surface outcomes, even when they share a star. That diversity is valuable because it helps separate the roles of starting materials, orbital position, and later, evolution. The system becomes a natural laboratory for rocky planet variety. One plausible formation pathway suggests that the system's planets formed in a disk where water ice was abundant beyond a TE snowline, with later mixing or migration delivering volatiles inward. That kind of transport is one way to explain water on close-in planets around cool stars. It points to a broader theme. Habitability can depend on early delivery routes, not just present-day orbit. The planet's current state may carry echoes of the disk's earliest structure. If TRAPPIST-1e has an atmosphere, its surface pressure could range widely, from Mars-like thinness to Earth-like thickness or beyond. Pressure controls whether liquid water can exist stably and how efficiently heat moves from place to place. It also affects how winds behave and how clouds form. A small shift in pressure can change the entire climate regime. On tidally locked worlds, cold traps on the night side are a special concern. Water vapor can migrate to colder regions and freeze, potentially building permanent ice deposits in darkness. If this happens too strongly, oceans could shrink and the climate could shift toward dryness. A thicker atmosphere can reduce this risk by warming the night side and smoothing extremes. If TRAPPIST-1e has continents, silicate weathering could act as a slow thermostat by drawing down CO2 over time. On Earth, weathering links climate to geology by removing greenhouse gas when conditions are warm and wet. On TRAPPIST-1e, the same principle could operate, that its effectiveness would depend on rainfall patterns, exposed rock, and circulation. Even the distribution of land could influence the planet's long-term stability. Volcanic outgassing could replenish CO2 and other gases, countering atmospheric loss to space. Volcanism can also supply water vapor and trace gases that change greenhouse strength. Whether outgassing is steady or episodic depends on internal heat and tectonic style. The planet's sky, if it has one, could be partly written by its mantle. Plate tectonics is unknown on TRAPPIST-1e, and it may instead operate in a stagnant lid regime where the crust does not break into drifting plates. Both styles can support volcanism, but they recycle material differently. Recycling affects how carbon and other volatiles move between surface and interior. Over long spans of time, this can shape whether a climate stays stable or drifts toward extremes. If TRAPPIST-1e has a thick atmosphere, heat transport could be strong enough that much of the planet stays relatively mild. If the atmosphere is thin, conditions could become sharply bimodal, with a hot day side and a deeply cold night side. The same incoming starlight can yield very different lived temperatures depending on atmospheric mass. This is one reason that habitable zone is only a starting frame. The planet's transit geometry makes it possible, in principle, to study its atmosphere using transmission spectroscopy. During a transit, a tiny fraction of starlight filters through the planet's atmospheric limb. Subtle patterns in that filtered light can hint at molecules, temperature structure, or haze. The signals are small, so confidence often requires repeated observations. Clouds and hazes can hide molecular features, making an atmosphere harder to identify even if it exists. A spectrum that looks smooth can mean no atmosphere at all, or it can mean a cloudy atmosphere that masks absorption lines. This ambiguity is common in exoplanet work. It pushes observations toward multi-wavelength strategies and careful modeling. The star's small size helps observationally, because a given atmospheric layer blocks a larger fraction of starlight than it would around a sun-sized star. This amplifies the relative signal in transit measurements. It is one reason M-dwarf systems are considered favorable for atmospheric searches. The same geometry that makes a star dim can make its planets easier to probe. If TRAPPIST-1e has water vapor, it could be detectable in principle, but interpretation can be complicated. Water features can overlap with other absorbers depending on temperature and cloud decks. Robust identification often requires multiple spectral bands and consistency across observations. The goal is not just a single hint, but a coherent atmospheric picture. Because the TRAPPIST-1 planets are close together, their gravitational interactions slightly shift transit times. Those timing shifts help infer planetary masses, which then inform density estimates. Density is one of the main clues to whether a planet is rocky, water-rich, or has a significant volatile layer. In compact systems, gravity becomes a tool as much as a force. A rocky composition supports Earth-like comparisons, but similarity is broader than rock alone. Atmosphere, oceans, and internal activity often matter as much as radius. TRAPPIST-1e's strongest appeal is that it clears an important first hurdle. It appears close to Earth in size and plausibly rocky. From there, the question becomes what kind of rocky world it actually is. The planet's equilibrium temperature is a rough estimate based on starlight and reflectivity assumptions. It is not a direct surface measurement, and it does not account for greenhouse warming or cooling from clouds. A planet with the same equilibrium temperature can still be hot, mild, or cold at the surface depending on its atmosphere. That gap between simple estimates and real climates is part of what makes these worlds so scientifically alive. If TRAPPIST-1e has a substantial ocean, it could moderate temperature and add stability through heat capacity. Water stores warmth and releases it slowly, smoothing extremes over time. On a tidally locked world, seasonal cycles may be weak, but ocean circulation can still create broad, steady climate patterns. Even small currents could matter when a planet's day and night are so asymmetrical. Light on TRAPPIST-1e would appear redder than Earth's daylight because of the star's spectrum. That changes surface reflectance behavior and can influence atmospheric photochemistry. It also affects how ice, water, and rock absorb energy. The color of starlight becomes a quiet but persistent climate parameter. The age of the TRAPPIST-1 system matters for habitability because time allows both stabilization and loss. Older systems can give planets long spans to develop secondary atmospheres and reach chemical equilibria. They also provide long spans for stellar winds and radiation to erode gases. In this balance, history becomes as important as present conditions. Because TRAPPIST-1e orbits close in, it is more exposed to stellar wind pressure than Earth is to the solar wind. That exposure can increase atmospheric escape processes, especially when the star is active. Escape is not only about heat, it is also about particles and magnetic interactions. The space environment becomes part of the climate story. If TRAPPIST-1e began with a hydrogen-rich envelope, it may have lost much of it over time. Losing hydrogen can shift a planet from a puffier, mini-Neptune-like state toward a denser, secondary atmosphere rocky world. That transition can define whether the planet ends up more Earth-like or more alien in structure. The present planet may be the result of the long, quiet shedding. Planetary albedo how much light. The planet reflexes a dominant unknown in many TRAPPIST-1e scenarios. A brighter planet can stay cooler under the same starlight, while a darker one warms more. Clouds, ice, and surface composition all shape albedo. In climate modeling, a small difference in reflectivity can open or close whole regions of parameter space. Some models explore terminator habitability, where temperatures near the day-night boundary could be moderate. This idea depends on atmospheric circulation and how sharply temperature falls from dayside to nightside. It also depends on topography and whether winds converge moisture into particular regions. The terminator becomes a possible corridor of steadiness in a world of extremes. If TRAPPIST-1e has significant CO2, it could prevent global freezing by trapping heat. At the same time, too much CO2 could push temperatures too high, depending on irradiation and cloud behavior. This is a delicate balance. Greenhouse gases can be protective in moderation and overpowering in excess. The same molecule can support habitability or destabilize it. If the planet is water-rich, high-pressure ice layers could exist beneath oceans, changing interior structure. In such cases, the planet could be Earth-like in size, yet unlike Earth in how ocean water interacts with rock. Nutrient cycling and geochemical exchange could be altered by thick ice mantles. The planet might look familiar in radius while behaving unfamiliar in chemistry. The atmosphere, if it exists, might be vulnerable to episodic stripping during extreme stellar events, rather than only slow, steady loss. That introduces a punctuated risk pattern, where long, quiet spans are interrupted by damaging bursts. It also complicates predictions, because a single rare event can shift an atmosphere's trajectory. Planetary habitability can hinge on both averages and extremes. If a biosphere existed, its detectability would depend on atmospheric stability and photochemistry. Many gases that look biologically interesting on Earth can also be produced through non-biological pathways under certain conditions. That means interpretation would require careful context, not one simple signal. The goal would be a consistent set of atmospheric clues rather than one isolated indicator. TRAPPIST-1e is a clear example of why Earth-like is a spectrum rather than a single category. It may match Earth's size, while differing strongly in starlight color, orbital period, and likely rotation state. Those differences can lead to climate regimes that Earth never experiences. Similarity in one dimension can coexist with deep difference in another. Future observations often focus not just on whether there is an atmosphere, but on the constraints that shape climate: mean molecular weight, cloud properties, and temperature structure. Even partial constraints can rule out many scenarios, narrowing the plausible range. With enough data, the planet can move from candidate toward a more physically pinned-down world. Each measurement is a gentle tightening of uncertainty. TRAPPIST-1e remains widely discussed because it combines relative proximity, favorable transit geometry, and a radius close to Earth's. That combination makes it one of the better cases for learning how small rocky planets behave around small stars. Even if it turns out to be inhospitable, it can still teach us what conditions are common and what conditions are rare. In that way, it becomes a quiet reference point for understanding Earth-like possibilities across the galaxy. Now we gently shift our attention to another quiet world, one that circles the closest star to our own Sun. Proxima Centauri b rests in a different kind of neighborhood, closer in space, yet shaped by conditions very unlike Earth's. As we explore it, we'll move slowly through what scientists have learned about its orbit, its star, and the subtle forces that shape its environment. Proxima Centauri b orbits the star closest to our own Sun, making it the nearest known world that falls within a temperature range often discussed in connection with surface liquid water. Its closeness in cosmic terms does not make it reachable, but it does make it feel less abstract than most exoplanets. Being part of the Alpha Centauri neighborhood gives it a special place in astronomical imagination. It is a reminder that potentially temperate planets can exist right next door on a galactic scale. This planet was discovered using the radial velocity method, which detects the subtle back and forth motion of a star caused by an orbiting planet's gravity. Instead of watching the planet pass in front of the star, astronomers inferred its presence from the star's shifting light. This technique measures the planet's minimum mass rather than its exact mass. Even so, the signal was strong enough to indicate a world roughly comparable to Earth in mass. Proxima Centauri B's estimated mass places it close to Earth's scale, though it could be somewhat heavier depending on its orbital tilt. A mass in this range suggests the planet could be rocky rather than gaseous. Rocky planets tend to have solid surfaces and more familiar physical processes. This mass range is one of the reasons Proxima b is often discussed alongside Earth-like candidates. The planet completes an orbit in only about 11 days, meaning its year is dramatically shorter than Earth's. This short year is a natural consequence of orbiting a faint red dwarf star. Around such a star, planets must be close in to receive enough warmth. The rhythm of time on Proxima b would feel compressed compared to Earth's slow seasonal cycle. Proxima Centauri b lies within what is commonly described as the star's habitable zone. This means that, under certain atmospheric conditions, surface temperatures could allow liquid water to exist. Being in the habitable zone does not guarantee habitability, but it does place the planet in a region of interest. It marks a balance point between too much and too little stellar energy. The star Proxima Centauri is an EM dwarf, much cooler and smaller than the Sun. Its light output is dominated by red and infrared wavelengths rather than visible light. This difference affects how a planet's atmosphere absorbs energy and how its surface warms. Life, if it existed, would experience a very different quality of daylight. One of the main challenges for Proxima Centauri b is its star's activity. Proxima Centauri is known for producing flares that release bursts of high-energy radiation. These flares can interact strongly with a planet's atmosphere. Over long periods, they may erode gases or alter atmospheric chemistry. Stellar flares can strip away protective atmospheric layers, especially ozone-like shields that block ultraviolet radiation. Without such layers, surface conditions can become harsher. Repeated exposure to energetic particles can slowly thin an atmosphere. This makes long-term atmospheric stability a central concern for Proxima b. Because of its close orbit, Proxima Centauri b is likely tidally locked or close to it. Tidal locking means one side of the planet always faces the star, while the other remains in darkness. This creates a permanent day side and night side. Such a configuration reshapes climate patterns in fundamental ways. On a tidally locked planet, the ability of the atmosphere or oceans to move heat becomes critical. Without heat transport, the day side could be extremely warm while the night side freezes. With sufficient circulation, temperatures can be moderated across the globe. Climate models explore many versions of this balance. If Proxima Centauri b has an atmosphere, water vapor could migrate toward colder regions and freeze. Over time, this could lock water away on the night side. A thicker atmosphere can prevent this by keeping temperatures more even. The fate of surface water depends on this delicate interaction. The planet's surface gravity depends on its true mass and radius, which are not both precisely known. Gravity influences how tightly an atmosphere is held. Stronger gravity helps prevent gases from escaping into space. It also affects how tall atmospheric layers extend above the surface. Because Proxima Centauri b orbits so close to its star, it is exposed to intense stellar wind. Streams of charged particles can collide with the atmosphere. Without protection, this interaction can drive atmospheric loss. A magnetic field could reduce this erosion, but its presence is uncertain. A planet's magnetic field depends on its internal structure and rotation. Slow rotation due to tidal locking can weaken magnetic dynamo processes. However, some models suggest dynamos may still operate under certain conditions. Whether Proxima b has such a field remains unknown. The planet's formation history plays a major role in its current state. If it formed farther from the star, it could have accumulated more water and volatiles. Later migration inward could have preserved some of that material. Alternatively, it may have formed close in and remained relatively dry. Some models describe Proxima Centauri b as potentially water-rich, perhaps even an ocean world. Large amounts of water would influence climate stability and heat transport. Water-rich planets behave differently from Earth, even if they share similar mass. The presence of deep oceans changes geology and chemistry. The radial velocity method can be affected by stellar activity signals. Star spots and magnetic cycles can mimic planetary signatures. Careful analysis is required to separate true planetary motion from stellar noise. Proxima b's detection involved extensive follow-up to confirm its reality. Because Proxima Centauri b is so close to Earth, it is often mentioned in discussions of interstellar exploration. Even optimistic concepts would take thousands of years to reach it. Still, its proximity makes it a reference point for imagining future technologies. It feels like a nearby destination in an otherwise vast galaxy. If the planet has an atmosphere, its composition could vary widely. It might be dominated by carbon dioxide, nitrogen, or other gases. Each composition leads to different greenhouse effects and climate outcomes. Without direct measurements, many scenarios remain possible. Direct imaging of Proxima Centauri b is extremely challenging. The planet orbits very close to a relatively bright star. Separating the planet's faint light from the star's glare requires extreme precision. Future instruments may attempt this, but it remains difficult. Clouds could strongly influence the planet's climate. Depending on their altitude and composition, clouds can cool or warm the surface. Persistent cloud cover on the day side could reflect starlight. This could stabilize temperatures despite close proximity to the star. EM-dwarf stars like Proxima Centauri tend to be more active in their youth. Early intense radiation could have stripped away early atmospheres. Even if the star is calmer now, the damage may already be done. This early history weighs heavily in habitability assessments. Atmospheric escape often removes lighter gases first, such as hydrogen. Over time, this can leave behind heavier molecules. This process can transform an atmosphere from a primordial state into a secondary one. Proxima b's current atmosphere, if it exists, may reflect this evolution. If the planet once had oceans, ultraviolet light could have split water molecules. Hydrogen would escape into space, while oxygen could accumulate. Such oxygen-rich atmospheres can form without life. This complicates the interpretation of oxygen as a biosignature. Long-term climate stability depends on whether the planet has a working carbon cycle. On Earth, this cycle links volcanoes, weathering, and oceans. On Proxima b, similar processes could exist, but only under specific conditions. Without them, climate may drift toward extremes. Volcanic activity could replenish atmospheric gases lost to space. Volcanism also releases heat and reshapes the surface. The level of volcanic activity depends on internal heat and tidal effects. Too much activity could be destabilizing, while too little could starve the atmosphere. Tidal heating from the star's gravity could add energy to the planet's interior. Moderate tidal heating can support geological activity. Excessive heating could drive extreme volcanism. The balance depends on orbital shape and interactions. Compared to Earth, Proxima Centauri b receives less visible light. Photosynthesis, if it existed, would need to adapt to redder illumination. Energy availability at the surface could be lower for Earth-like plants. This changes assumptions about biological productivity. Climate patterns on Proxima b would differ from Earth's familiar jet streams. On a locked planet, circulation often flows from the day side to the night side. This can create strong winds and stable weather zones. Weather becomes organized by longitude rather than latitude. If the atmosphere is thin, temperature contrasts could be severe. The day side might become hot, while the night side freezes. Dust and gas could be transported across the terminator region. Such conditions would feel stark and unbalanced. If oceans exist, evaporation would be strongest on the warm day side. Moist air could rise and form clouds that reflect light. Rainfall might be concentrated in limited regions. Other areas could remain dry or frozen. Proxima Centauri is part of a multiple star system when considered alongside Alpha Centauri A and B. Long-term gravitational interactions appear stable. For Proxima b, stability over billions of years supports the possibility of long-lived climates. Chaos does not appear to dominate its orbit. Monitoring stellar flares helps scientists estimate atmospheric risk. Proxima Centauri has been studied closely for this reason. Understanding the star helps interpret the planet's chances. Stellar behavior becomes part of planetary science. Even though Proxima b lies in the habitable zone, it could still be airless. Habitable zones describe energy balance, not atmospheric survival. Mars shows how a planet can sit in the right region and still lose most of its air. This caution applies here as well. High surface reflectivity could keep the planet cooler. Ice or bright minerals would increase albedo. But too much ice could push the planet into a snowball state. Greenhouse balance becomes critical. If Proxima b is water-rich, thick ice layers may form at depth. These layers can isolate the ocean from the rocky mantle. Nutrient exchange would be limited in such a structure. Habitability would differ from Earth's surface-based ecosystems. Atmospheric models often treat Proxima b as a test case for EM-dwarf planets. Results vary widely depending on assumptions. This diversity reflects genuine uncertainty rather than disagreement. The planet sits at the edge of what current knowledge can resolve. Because its mass is a minimum estimate, the planet could be heavier than expected. Higher mass could mean stronger gravity and thicker atmosphere. It could also suggest more volatiles. Small differences in inclination matter greatly for interpretation. If the planet has continents, climate zones would be arranged differently than on Earth. Land near the substellar point could be warm and wet. Land on the night side could be permanently frozen. Geography would shape habitability patterns. Brightness variations of the star over time could drive climate variability. Long-term cycles may exist alongside short flares. These changes can influence atmospheric chemistry and surface conditions. Climate may not be steady even if average conditions seem mild. Detecting life on Proxima b would be extremely difficult. Signals could be masked or mimicked by non-biological processes. Scientists emphasize context and multiple lines of evidence. Caution is central to interpretation. Proxima Centauri b is often called Earth-like because of its mass and location. Yet its environment is fundamentally different from Earth's. It highlights how Earth-likeness is not a single property. It is a balance of many interacting factors. Research continues to refine stellar properties and planetary parameters. Each improvement reduces uncertainty slightly. Over time, the picture of Proxima b becomes clearer, even if it remains incomplete. Knowledge accumulates quietly. Proxima Centauri b stands as a nearby example of a world that could resemble Earth in some ways and diverge strongly in others. It teaches that proximity does not guarantee familiarity. Even the closest stars can host worlds shaped by very different rules. In that contrast, the planet offers calm insight into the diversity of rocky worlds. We now drift farther outward, toward a planet discovered in the distant field of a long, patient telescope. Kepler-186f moves quietly around a small red star, far beyond the reach of direct observation. What we know about it comes from delicate measurements and careful inference, revealing a world that is subtle, distant, and quietly intriguing. Kepler-186f is known primarily because it passed in front of its star from our point of view, causing a tiny, regular dimming of starlight. This method of discovery reveals the planet's size with care and precision, but leaves many other properties open to interpretation. From this single repeating signal, scientists begin to reconstruct an entire world. Much of what follows is built from patient reasoning rather than direct measurement. The planet's radius is only slightly larger than Earth's, placing it firmly in the category of Earth-sized or near-Earth-sized worlds. This similarity in size suggests a rocky composition rather than a gaseous one. Rocky planets tend to have solid surfaces and layered interiors. Even so, size alone does not reveal what the surface actually looks like. Kepler-186f orbits a small, cool red dwarf star, far dimmer than the Sun. Because the star is faint, the planet can orbit relatively close and still remain cool. This relationship between star brightness and orbital distance defines where temperate conditions might arise. It also means the planet's environment is shaped by a very different kind of starlight. The planet's orbit takes many tens of days, longer than the ultra-short orbit seen in some compact red dwarf systems. This longer year suggests a slightly wider separation from the star. That distance may reduce some tidal effects, though tidal locking can still occur around small stars. The rhythm of time on Kepler-186f is slower and more measured. Kepler-186f lies near the outer edge of its star's habitable zone. This placement means it receives less energy than Earth receives from the Sun. As a result, its climate would depend strongly on atmospheric composition. Without sufficient greenhouse warming, surface temperatures could be quite cold. Because the planet is hundreds of light-years away, it cannot be studied in detail with current instruments. Its atmosphere, if it exists, remains hidden from direct observation. Scientists rely on models to explore what conditions might be possible. Distance adds a layer of quiet uncertainty to everything known about this world. The host star emits most of its energy in red and infrared wavelengths. This changes how ice, rock, and water absorb heat. Ice, under redder light, may reflect less energy than ice under sunlight. This subtle difference can influence whether a planet freezes or remains temperate. Kepler-186f's mass is not directly measured, only inferred from its size. Without a precise mass, its density remains uncertain. It could be a dense rocky world like Earth, or a rock and water mix with a lower average density. This ambiguity leaves room for multiple interior structures. If the planet is tidally locked, one hemisphere may face the star continuously while the other remains dark. In that case, climate patterns would be dominated by permanent day and night regions. Atmospheric circulation would determine whether heat can spread evenly. Such circulation becomes the quiet engine of habitability. If the planet is not tidally locked, it could experience a more Earth-like cycle of day and night. This would allow for more familiar temperature patterns. However, even then, seasons would depend on axial tilt, which is unknown. Many fundamental rhythms remain hidden. The star's early history likely included periods of stronger activity. During those times, high-energy radiation could have stripped away early atmospheres. Whether Kepler-186f retained or rebuilt an atmosphere afterward is unknown. Its present state may be the result of long-ago losses. If the planet has an atmosphere today, it may be dominated by carbon dioxide. A CO2-rich atmosphere could provide enough greenhouse warming to keep surface water liquid. This would be especially important given the planet's lower energy input. The balance between cold starlight and greenhouse warmth is central. Clouds on Kepler-186f could play a major role in regulating temperature. Depending on their altitude and thickness, clouds can either cool or warm the surface. Under red dwarf light, cloud behavior may differ from Earth's. This adds complexity to climate predictions. If the planet has oceans, they could store and transport heat across the surface. Ocean circulation can soften temperature extremes over long timescales. Even slow-moving currents can matter on a world with limited sunlight. Water becomes a quiet stabilizer. If instead the planet is land-dominated, temperature swings could be more pronounced. Land heats and cools more quickly than water. This could lead to harsher climates, especially near the edge of the habitable zone. Geography would quietly shape survival conditions. Kepler-186f may experience limited atmospheric escape compared to closer-in planets. Its wider orbit reduces exposure to stellar wind. This could help preserve heavier gases over time. Atmospheric longevity improves the chances of long-term climate stability. The planet's interior heat depends on radioactive elements and formation history. Internal heat drives volcanism and tectonic processes. Without sufficient heat, geological activity may fade. This affects how gases are recycled into the atmosphere. If volcanism exists, it could replenish carbon dioxide and other gases. This replenishment can counteract atmospheric loss. Over geological time, volcanism helps regulate climate. The surface and interior remain quietly connected. Plate tectonics, if present, would further stabilize climate by cycling carbon between surface and interior. On a slightly larger planet, tectonic behavior may differ from Earth's. Higher gravity can change how plates move or whether they exist at all. The outcome remains uncertain. If Kepler-186f is water-rich, thick layers of high-pressure ice may form beneath the ocean. These layers can isolate liquid water from the rocky mantle. Nutrient exchange would be limited in such a configuration. Habitability would follow unfamiliar rules. The planet's discovery was important because it demonstrated that Earth-sized planets exist in habitable zones around red dwarfs. This shifted scientific expectations. It suggested such worlds may be common rather than rare. Kepler-186f became a quiet milestone. Because the planet's transit signal is small, detecting it required long, careful observation. Multiple transits had to be recorded to confirm its presence. This patience reflects the subtlety of small planet detection. The signal was faint but consistent. Kepler-186f's location in the sky places it in the region observed continuously by the Kepler telescope. That long, uninterrupted stare made detection possible. Without such extended observation, the planet would have remained unseen. Time itself was part of the instrument. The planet's potential atmosphere would likely be thinner or denser depending on its gravity and composition. Atmospheric pressure shapes weather, cloud formation, and heat transport. Small changes in pressure can produce large climate differences. This sensitivity adds to uncertainty. If the planet has ice-covered regions, their reflectivity under red light may be lower than Earth's ice. This could reduce cooling feedback and help maintain warmth. Such details illustrate how star type subtly reshapes climate physics. Familiar materials behave differently under unfamiliar light. Kepler-186f may have experienced periods of global glaciation. Near the outer edge of the habitable zone, small changes can trigger widespread freezing. Escaping such states would require greenhouse gas buildup. Climate history may include long frozen epochs. If the planet avoids full glaciation, it might host liquid water near the equator or substellar regions. These zones could remain stable even if other areas freeze. Habitability could be regional rather than global. Life, if present, would adapt to narrow bands. The planet's atmosphere could shield the surface from radiation, depending on thickness and composition. Even a modest atmosphere can provide significant protection. Radiation shielding is essential for long-term surface stability. This protection works quietly over billions of years. Kepler-186 EFS distance makes it a low-priority target for near-term atmospheric characterization. New generations of telescopes may eventually reach such distant systems. For now, it remains a world known mostly through inference. Its silence is part of its nature. The planet's discovery helped refine estimates of how common Earth-sized planets are. Statistical studies include Kepler-186f as part of a broader population. Each such planet adds weight to the idea that rocky worlds are abundant. The galaxy appears rich in quiet stones. If Kepler-186f rotates slowly, its atmospheric circulation may be dominated by large, stable cells. These patterns could persist for long periods. Weather would be steady rather than chaotic. Stability becomes a defining trait. If the planet rotates more quickly, winds could redistribute heat more dynamically. Faster rotation introduces Coriolis's effects and jet streams. These processes shape cloud belts and temperature gradients. Even rotation speed alters climate personality. Kepler-186 EFS potential biosignatures, if any existed, would be extremely difficult to detect. Distance weakens signals and increases noise. Any interpretation would require extraordinary caution. The planet teaches humility in the search for life. The concept of Earth-like applied to Kepler-186f refers mostly to size and orbit. Surface conditions could be vastly different. Earth-likeness is a starting comparison, not a conclusion. Similar numbers can hide deep differences. As models improve, Kepler-186f continues to appear in simulations of red dwarf habitability. Each model explores a slightly different combination of parameters. Together, they form a wide envelope of possibilities. The truth may lie quietly within that range. Kepler-186f represents a class of planets that are common yet distant. They are not dramatic or extreme, but quietly persistent. Their importance lies in what they suggest about planetary abundance. Ordinary worlds may be the rule. Though much about Kepler-186f remains unknown, it stands as a reminder that gentle, Earth-sized planets can exist far from our reach. Its story is incomplete, but not empty. In its distance and subtlety, it invites slow contemplation of how many such worlds may circle faint stars throughout the galaxy. At last, we turn toward a heavier, slower world, one that moves with calm regularity around a dim red star. LHS 1140b invites a quieter kind of attention, shaped by deep time, steady orbits, and long-term balance. Its nature is less dramatic and more enduring, offering a reflective look at how rocky planets may settle into stable states, far from sudden change. LHS 1140b is classified as a super-Earth, meaning it is larger and more massive than Earth, but still far smaller than gas giants. Its size places it near the boundary where rocky planets transition into worlds rich in volatiles. This position makes it especially interesting because small differences in composition can lead to very different outcomes. The planet may be rocky at heart, or it may carry deep layers of water and ice. The planet was discovered because it transits its star, passing directly between the star and our line of sight. This geometry allows astronomers to measure its radius with precision. Transiting planets provide rare opportunities to probe atmospheres and orbits. LHS 1140b stands out because it combines transit visibility with temperate conditions. Its host star is an EM dwarf, cooler and smaller than the Sun, emitting most of its energy in red and infrared light. Around such stars, habitable zones lie close in. LHS 1140b orbits at a distance that allows it to receive modest, steady energy. The light bathing the planet would feel dim and reddish compared to Earth's daylight. The planet's orbital period is measured in weeks rather than days, giving it a slower rhythm than many closing red dwarf planets. This wider orbit reduces some extreme tidal effects. It also places the planet firmly within the star's temperate zone. Time on LHS 1140b flows gently rather than rushing. Measurements of mass and radius suggest LHS 1140b is dense, supporting the idea of a solid, rocky interior. However, its density also allows room for substantial water content. A planet can be rocky and still carry deep oceans. The interior structure may be layered and complex. If the planet is water-rich, it may host a global ocean tens or hundreds of kilometers deep. Beneath that ocean, high-pressure ice could form, separating liquid water from rock. This would change how heat and nutrients move through the planet. Such a world would be Earth-like in size, but not in structure. LHS 1140 star is considered relatively calm compared to many red dwarfs. Its slower rotation is often linked to lower magnetic activity. Reduced stellar violence can help a planet retain its atmosphere. Quiet stars offer gentler long-term environments. The calmer stellar environment may have allowed LHS 1140b to keep a thick atmosphere over billions of years. Atmospheric survival is one of the biggest challenges for close-in planets. Less radiation means slower erosion. Stability builds quietly over time. The planet's gravity is stronger than Earth's due to its higher mass. Stronger gravity helps hold onto atmospheric gases. It also compresses the atmosphere, lowering its vertical extent. The sky on such a world would feel heavier. Higher gravity also affects surface features. Mountains may be shorter and broader. Landscapes would feel flatter, shaped by weight and pressure. Even erosion would follow slightly different rules. If LHS 1140b is tidally locked, one hemisphere may always face the star. In that case, climate patterns would revolve around permanent light and darkness. Heat transport would become essential. Stability would depend on atmospheric and oceanic circulation. If the planet rotates slowly but is not fully locked, it may still experience long days and nights. This would soften temperature contrasts. Slow rotation favors stable, large-scale weather patterns. The atmosphere would move deliberately rather than chaotically. Because the planet transits, its atmosphere may eventually be studied using spectroscopy. During transit, starlight filters through the atmospheric edge. Tiny imprints in that light can hint at gases present. This makes LHS 1140b a key observational target. A thick atmosphere could keep surface temperatures above freezing, even with limited stellar energy. Greenhouse gases trap heat efficiently over long periods. A dense atmosphere acts like a thermal blanket. warmth accumulates slowly and remains. If the atmosphere is thinner, surface water may freeze except in limited regions. On a locked planet, the substellar area could remain warm enough for melting. Habitability might exist only in certain zones. Life, if present, would adapt to narrow niches. Ocean circulation could transport heat from warm regions to colder ones. Even slow currents matter over long timescales. Water moves energy quietly and persistently. Oceans smooth extremes without drawing attention. If the planet is mostly ocean-covered, land exposure may be limited. Reduced land area affects carbon cycling. Weathering processes could be weaker or slower. Climate regulation would follow unfamiliar paths. If continents exist, their distribution would strongly influence climate. Land near the star-facing side could be warm and wet. Land on the dark side could be frozen. Geography would divide the planet into long-lasting climate regions. The interior heat of LHS 1140b depends on its formation and composition. Radioactive decay can sustain warmth over billions of years. Internal heat drives volcanism and tectonics. Without it, geological activity fades. Volcanic outgassing can replenish atmospheric gases. This process counters losses to space. Over long spans of time, volcanism supports atmospheric persistence. The planet's surface and sky remain linked. Plate tectonics, if present, would further regulate climate by recycling carbon. On super-Earths, tectonic behavior is uncertain. Higher gravity may either promote or suppress plate motion. The outcome depends on mantle strength and heat flow. If tectonics are absent, the planet may operate with a stagnant lid. In such worlds, volcanism occurs through localized upwellings. Atmospheric regulation still occurs, but less dynamically. Change happens slowly. LHS 1140b's orbit appears stable over long timescales. Stability allows climates to persist without violent shifts. Orbital calm is a quiet foundation for habitability. Chaos does not dominate this system. If additional planets exist in the system, their gravitational influence could shape eccentricity and tides. So far, LHS 1140b appears dynamically well-behaved. This supports long-term equilibrium. Stability accumulates over time. The planet likely experienced a more active stellar phase early in its history. Even so, its higher gravity and calmer star may have limited atmospheric loss. Early survival shapes everything that follows. The present is written by the past. Atmospheric composition may include nitrogen, carbon dioxide, and water vapor. Each contributes differently to pressure and temperature. The balance between them determines climate personality. Subtle shifts matter greatly. Clouds may form persistently over warm regions. Depending on altitude, they could reflect light or trap heat. Clouds act as regulators rather than decorations. Their role is central, but hard to observe. Because the star emits redder light, ice and snow behave differently than on Earth. Reflectivity may be lower, allowing ice-covered regions to absorb more heat. This can help prevent runaway freezing. Small, spectral differences matter. If the planet enters a partially frozen state, subsurface oceans could still exist. Liquid water beneath ice can persist for long periods. Habitability does not require open seas. Life, if present, may be hidden. The planet's atmospheric pressure could be significantly higher than Earth's. Higher pressure improves heat transport and radiation shielding. It also affects chemistry and cloud formation. The air itself becomes a stabilizing force. Radiation reaching the surface would be filtered by the atmosphere. Even under a red dwarf star, sufficient shielding can protect the surface. Calm skies reduce long-term damage. Protection is quiet and cumulative. LHS 1140b is often described as Earth-like because of its temperate orbit and rocky potential. Yet it may differ profoundly in ocean depth, gravity, and geology. Similar labels hide deep diversity. Earth-like is a starting metaphor, not a destination. Its relative proximity compared to distant Kepler planets makes it more accessible to future study. Repeated observations can refine measurements. Over time, uncertainty shrinks. Knowledge grows patiently. If life existed on LHS 1140b, its signatures might differ from Earth's. Different light, chemistry, and pressure shape biology. Familiar biosignatures may not apply. Interpretation would require caution and context. False positives remain possible in atmospheric analysis. Oxygen and other gases can form without life under certain conditions. Understanding the planet as a system is essential. No single signal tells the full story. LHS 1140b represents a class of worlds that change slowly. Its mass, orbit, and star favor long-term persistence rather than rapid evolution. Such planets may be common. Quiet stability may be the norm. The planet's story unfolds over billions of years rather than dramatic moments. Its climate, interior, and atmosphere evolve gradually. Nothing happens quickly here. Time smooths edges and extremes. As we consider LHS 1140b, it invites reflection on endurance rather than excitement. It is a world shaped by patience. In its steady orbit and muted light, it reminds us that habitability may often arise not from perfect conditions, but from long-lasting balance. And so we rest gently with this final world, letting its slow orbit and quiet persistence drift through our thoughts. The universe holds many planets that do not rush, do not flare brightly, and do not demand attention. They simply exist, steady and calm, moving through deep time in silence.